Welcome back to my course, the Industrial Biotechnology. Now, I am going to discuss that upstream processing. As you know that in the fermentation industry, that one important aspect is the sterility. And sterility, when we concern about the sterility, that we try to find out what is the possible avenue through which we can have the contamination problem. And one main culprit is the air, and second is the media, and third is the maybe your fermentation vessels. So, so everything should be sterilized, because whatever we do, that everything should be sterilized. So, air sterilization is a very important aspect, because most of the biochemical industries, they are operated under aerobic conditions, and I told you that microorganism can take the oxygen which is dissolved in the media. They cannot take the oxygen which is present in the air. So, the mass transfer of the oxygen to the fermentation media is very important, and so since the oxygen is sparingly soluble in water, so we have to sparge the air more and more, so that more oxygen transfer takes place, so that limitation problem of the dissolved oxygen limitation problem can be overcome. So, since we are passing air more and more, there is a possibility of contamination problem in the fermentation process. So, so question comes, how we will sterilize the air. Now, for an effective aerobic fermentation process, air should be completely sterilized and sterile and free from all microorganisms and suspended particles. There is a wide variation in the quantity of suspended particles and microbes in the atmospheric outdoor air. Now, here I want to tell you a couple of things, that particular one thing I want to mention, that biochemical industry usually should be located in little bit higher altitude. And why it is higher altitude? Because if you go to the higher altitude, the particulate matters present in the air will be less, and also you should not be in the metropolitan cities where you have particulate matter concentration in the air is very high. Because why? The reason is that these particulate matters, they are the carrier of microorganisms. So, more microorganism present in the air, so your sterility of the sterility problem will be more. So, it is usually prescribed that you should be in a place where you have less particulate matters present in the air. Now, the microorganism may be in the range of 10 to 2000 per cubic meter, while the suspended particles might be 20 to 100 about the 10,000 per cubic meter. Among the microorganisms present in the air, fungal spores 50%, gram-negative bacteria 40%, they are the dominants. Now, airborne microbes, now question comes that what kind of microbes removal you are required in your system. That is very important. I work with the citric acid industry, and we found that in our fermentation process, our main culprit is the yeast cells. And when we use any kind of sterility process, then we should always target that what kind of organism you are going to remove, and this can be removed in different ways. You can remove, I will discuss the different process one after another. This mainly consists of species of bacteria, bacterial spores, yeast, fungi and viruses. The size of this organism varies from 0.5 to several hundred microns. The airborne particles which have to be destroyed or collected during the air sterilization are about the size of small bacteria, namely 0.5 to 1 microns. Now, what are the sterilization technique that we have? Air sterilization technique that we have. We have physical separation technique, what we call filtration, And filtration can be done in so many ways. We can use the fibers, we can use kind of membrane through the physically you can separate, and there is the heat. But heat is not suitable for sterilizing the air, because air is a non-conductor of heat. So you require a higher amount of heat for removing the contaminants. And then UV rays. Now two type of air we shall have to sterilize. One is stagnant air and this moving air. Now when you talk about that any kind of fermenters, so in sparging air, this is the moving air. The air is passing, you have to sparge through the sparger. So for that usually we use the kind of physical separation technique, what you call filtration. But in case of stagnant air, we use some either UV rays or germicidal space. As for example, we know that in the operation theater in the different hospitals, and there this is usually that should be jumpy, and then that they usually do with the help of UV rays. But in the fermentation industry, like I can give the example of cheese making industry, that where the cultivation is usually done in the open vat, because the curd formation usually take place in the open vat, and the room should be sterilized, and this sterilization of the stagnant air is done with the help of germicidal spray. Germicidal, I can give the one example of chlorine. Chlorine is has very good germicidal effect. It gives it kill the contaminants to a great extent. So this is the thing that we have. So here in this lecture, mostly I shall concentrate on the this air, that is contaminants present in the moving air, that because heat is no good for the heat sterilization of the air. So filtration is kind of physical separation process through which we can separate the particulate matters or cell present in the air. Now that filtration, we have two types of filter we use. One is called depth filter and this is the membrane filter. A depth filter is a filter consisting of either multiple layer or single layer of media having the depth, which captured the contaminants within the structure as opposed to on the surface. Let me give the very simple example. Suppose I told you glass wool fiber. Glass wool fiber. Now glass wool fiber is looking like this. So suppose you have this is the here we put some kind of mesh here, and this is the glass wool fiber. So we can compress, we can make it complex, we can uncompress also. If you make it complex, your pore size will be minimum, and in uncomplex will be pore size will be more. So as per your requirement, as for example, I told you I work with the citric acid industry, and our main culprit is the yeast cells. Our main culprit is not the bacterial cells. The yeast cells has the size about 3 microns to 7 microns. 7 microns. So if the pores we compress in a manner so that yeast should be removed. Most of the yeast, even some bacteria particular through the filter doesn't affect our process to a great extent. So this is the depth filter that we have, and membrane filter is very simple, that we have a membrane here, and the membrane has some pores, and inside the pore as per so basic difference between the membrane filter and the depth filter is that membrane filter we have some lot of operational problem, because if we reduce the size of the pore, then life of the membrane, because the pressure across the membrane will be very high. If pressure across the membrane is very high, then the life of the membrane will be reduced to a great extent, because and not only that, fouling of the membrane surface and other things, regeneration of the membrane, that will be very difficult. Those are the problem we have very problem because in case of membrane filter. That is why industry particularly in the fermentation industry, we go for depth filter as for example glasswool filter we use. Now in the depth filter is the air pass through a glasswool containing the depth filter and particles are trapped and removed. The filtration techniques primarily involve physical effect of inertia, blocking, that gravity, static attraction, electrostatic attraction, and the diffusion. That I shall explain one after another how it is done. That first let us so we have the inertial impaction, we have diffusion, we have interception, we have electrostatic attraction, and the gravitation, how it is the particle separation take place. So single fibers, we can assume that single fibers, and it is if I take the cross section, this is a fiber, and if you take the cross section, it looks like this. It is a circular and cross. Now at the perpendicular to the, if the air is flow like this, we can do the analysis of the system like this. So we make this like this single cylinder fiber is placed perpendicular to the aerosol flow in an infinite space, and that the airflow around the cylinder is lamellar with no vortex. The following analysis is the two-dimensional. The inertial impaction, let me tell you what you call the inertial impaction. The suspended outer particle in a airstream has a momentum. Now air in which the particles are suspended will flow through the filter by the route of less resistance. However, the particles because of their momentum tends to travel in straight line. Now we know Newton's first law of motion, and first law of motion says that every particle try to move in the same direction because due to inertia of forces. Now if your inertia force is very high, because there is the minimum velocity of the airstream is required for having this inertial impaction. If you have more than that, then what will happen here, you can see the particle is moving. Normally it is moving like this and touching the surface like this. When you say the inertial impaction, instead of moving this path, it will follow the straight path, because this is the part, your air is flowing straight. So the inertia, instead of going this way, it will follow the straight path and deposit it on the surface of the solid matrix. And this is called, if the particle collected through this, we call it particle collected due to the inertial impaction. So if you look at here, the flow pattern of the particle deviate from those of the airflow due to the inertia of the particle as they approach the cylinder, because this happens due to the high velocity of the fluid. Now in the figure, the width of the upstream is denoted as B, and particles that are moved in the streamlines of air beyond B will not touch the cylinder surface, even after they deviate from the air streamline near the cylinder. Then the collection efficiency of single fiber due to inertial impaction is usually expressed B by dF. What is B? B is the the effective width. So what I want to know that this is which width of this airstream is effective. Maybe this is effective for here. If you, as you know, that if there is a particle present there, then it can straightway deposited on the surface of this fiber. This is like this. That is why we consider this is a effective width of the airstream, and diameter of the fiber is, this is the diameter of the fiber. So collection efficiency of single fiber due to inertial effect of the particle is zeta equal to B by E by dF. Now here the eta will be equal to 0 when psi is equal to 1 by 16. What is psi? Is called inertial parameter. This is equal to C into rho p dp square V0 into 18 mu into dF. The C is the Cunningham correction factor, rho p is the density of the particle, dp is the particle diameter, df is the fiber diameter, and rho is the viscosity of the air. The critical velocity is equal to that is this one. That means if the velocity is more than the critical velocity, then and only then your particle will collect it through the inertial impaction. That is the main thing over here. Then let me explain what we call interception. Interception means that when particle moves here in this line, the particle intercept with the fiber, just deposited on the line. It is there. Now, when it is possible, suppose suppose the particle is going like this. Now, if this particle radius is equal to this width, then and only then it will touch the surface of the fiber. Otherwise, it will not touch the surface of the fiber. So, this is if the particle is collected like this, we call it the particle collected due to the interception. So, this occurs by several mechanisms. More than one particle may arrive at a port simultaneously, and irregularly shaped particles may breach a pore, and once a particle have been trapped by a mechanism other than the interception, the pore may be partially occluded, enabling the entrapping of smaller particles. So, this is a problem that we have. Now, this efficiency can be expressed, but the collection efficiency due to interception is expressed like this. Now, here we come across the one geometrical new term, what we call geometrical ratio. What is the geometrical ratio? Geometrical ratio is nothing but diameter of the particle divided by diameter of the fiber. This is called geometrical ratio. And NRE is the Reynolds number. Reynolds number is the flow characteristics of the fluid. The du rho by mu. This is df is the diameter of the fiber, v is the velocity of the liquid, that is the air, and rho is the density of air, and mu is the viscosity of air. Now, diffusion is something different. This is usually take place at a very low velocity of air, because then the particle moves in the Brownian movement. Why? What is the Brownian movement? This particle strike this particle again strike this particle, again strike this particle. Ultimately, it deposited on the surface of the solid matrix. And if the particle deposited with the solid matrix like this, we call it particle collected through the diffusion. The extreme small particles suspended in the air are subjected to Brownian movement, which is randomly randomly movement due to collision with the fluid molecules. So, if I want to draw like this, that plot this overall collection efficiency versus the velocity of the fluid, the superficial velocity of the fluid, we can have the plot like this. So, this is very important, because that here you have three different sections, that this is here, this is 1, this is 2, this is 3. So, here the particle mostly collected due to the diffusion, this is the interception, and this is mostly due to the inertial impaction at the high velocity. This is but here again there is a called critical velocity, because in case of inertial impaction we have come across one critical velocity. What is that critical velocity? Above which the particle collected due to the inertial impaction. Because but this critical velocity is what? Because above this velocity, if you keep on increasing the velocity of the air, a time will come that your dragging force of the air is so high that it take the particle out from the fiber. So, what will happen? The performance of the fiber will take down. So, for designing of air filter, we shall have to always consider this critical velocity. The velocity when you design, under no circumstances the air velocity should be more than this. The air velocity should be always less than that. This is the, for designing is very much essential. Now, particle, that overall collection efficiency due to this diffusion is expressed like this. Now, here in case of interception we use NR, and now NR is the geometrical ratio. Now, this is usually replaced by 2x0 by f. Now, 2x0 is represented as displacement of the particle, that is called how much path is moved, that is 2x0, and then the collection efficiency is calculated like this. So, it is exactly similar to the same as our particle collected. So, the interception, only the difference is that your dp is replaced by 2x0. Now, particle also can be collected with the help of electrostatic attraction, but it is insignificant. Why it is insignificant? It has been found that there are different organisms, like I can give a typical example of Bacillus subtilis, that if you look at the charge distribution of Bacillus subtilis is different, that maybe 70% is maybe neutral, maybe positive, maybe the 20% might be the other charge, and 10% might be the other charge. That that if the distribution of the charge of this organism is different, then naturally even your fiber has a particular fiber, is only one charge, maybe positive charge. So, if it is positive charge, it will attract only the negative charge. Now, if your particles has both positive, negative and neutral charges, so it is the electrostatic particle separation due to the electrostatic attraction can be neglected. Now, since in the air filter we target the smaller particle, and smaller particle has very low density, so the particles separated through gravitation also can be neglected. So, so usually the overall collection efficiency can be expressed at eta 01 dash, eta 02 dash, eta 03 dash. So, this is collection efficiency due to inertial impaction, due to interception and due to diffusion. Now, question comes that what are the selection criteria for choosing this air filter? There are several selection criteria through which we can select the air filter. One is the filter retention efficiency. What is the efficiency of the filter? This is plays very important role. Then economy of the operation, because how much money we are going to spend for that. Age of filter use, how easily we can use the filter, and service provided by the manufacturer. This is very important because these factors that affect the selection criteria of the air filter. The most important selection criteria, filter efficiency and reliability of the organism retention. In this regard, the fixed submicron pore size membrane provides the highest level of filtration efficiency. Now, I was saying that there is a term called absolute filter. Absolute filter means what? That suppose when we use the membrane has a definite pore size, the 0.5 microns. So, if you 0.5 microns, whatever particle has more than 0.5 micron, that retain in the fiber. So, all the particles will be removed in this. That is the absolute filter that we have. Now, and use the hydrophobic filter material minimizes or eliminate the concern of filtered wetting due to the air moisture content. This is another important characteristics we have. Now, here when you talk about the depth filter, that I was talking about the glass wool fiber. Now, question comes, why we are selecting the glass wool fiber? Why not jute fiber? Why not the cotton fiber? The reason is that that if you I told you there is a term called drag coefficient. Now, drag coefficient in case of particular one Reynolds number when we use that in case of glass wool fiber and in case of this in jute fiber or cotton fiber, the drag coefficient in case of cotton fiber or jute fiber is much high as compared to that of glasswool fiber. And this drag coefficient, again this is correlated with the pressure drop across the filter. If the pressure drop is more across the filter, then there will be friction, because more friction, then more will be the pressure drop. Less friction, less will be the pressure drop. The more friction means that more heat will be generated. Now, if more heat generated, in case of jute fiber and cotton fiber, it will catch fire very easily. But in case of glasswool fiber, it can withstand high temperature, so it will not catch fiber so easily. So that is the advantage that we have. So that is the one reason we use the glasswool fiber in the industry. This is the depth fiber. The rate of removal of the particle can be expressed like this: dn by dx. X is the filter depth, and n is the concentration of the particle. This is follows the first order kinetics, and we can express like this. This is n by n0. How we can express like this? Then we can have this E value that we can easily calculate, and we can find out for 90% removal what is the expression will be 2.303 divided by K. That now if you plot this K value, that is the removal efficiency, that is with the linear velocity keep on increasing with that, then it is a decreasing. That your efficiency also increases, but again removal will be affected, because at the higher velocity what is happening? At the higher velocity, I told you the drag force is so high, it will detach the particle from the glasswool fiber and it will take it out. Now the increase of K with the increase of air velocity is probably due to increase of impaction, and illustrating the importance of contribution of the mechanism makes to the removal of the microorganism. The decrease of K value at the higher velocity is probably due to the disruption of the filter, allowing the channel to develop and fiber to vibrate, and resulting the release of previously captured organism. So there is a problem here, and it is required to provide 20 cubic meter fermenter with air at a rate of 10 cubic meter per minute for a fermenter lasting 100 hours. From an investigation, the filter material to be used, the optimum linear air velocity was shown as 0.15 meter per second, at which the value K value is suppose 1 point, but K should be the small k, by mistake it is capital K. This is 1.535 centimeter inverse. The dimension of the filter may be calculated as follows. This is very simple. So we can calculate that. We can n by n0 equal to K into x. Then we can find out how much, what is the n0 value. How we can calculate we have this. We assume the air contains about 200 microorganisms per cubic meter. Now how much the air is there? 10 cubic meter per minute. Then multiplied by 60 minutes, so hour. Then 100 hours we want to operate. So we will find out how much microorganisms is there. Then we find out what is the n value we want to, because acceptable degree of contamination 1 in 1000. This I want to point out, when we design any kind of air filter, we shall have to assume that what we are going to do, 1 out of 100, 1 out of 10,000, 1 out of 100,000. So as per your the process is concerned, you can decide on the basis of that. You can design your air filter, and if you put this value, you can find out the value of x. X is nothing but the depth of the air filter. This is coming about 15.12 centimeter. Then again, if you calculate this the diameter of the tubes, you can find out this is coming at 0.59 meter. And then the membrane filter I already talk about. Only examples are cellulose nitrate and cellulose diacetate, polycarbonate and polyester that is used. The pore size ranging from 0.051 micron to 12 microns. Only the problem is that I told you that in case of membrane filter, life is very short, because maintenance cost will be very high, and as you know that operational cost depends on the pressure drop across the particular in the process. In the pressure drop in case of membrane filter is very high, so our operation cost will be very high in case of, so that is not usually adopted in the industry. Thank you very much.